Welcome to Blacoh University. I'm Gary Cornell. Today we're going to be discussing positive displacement pumps and the role that pulsation dampeners can play in their operation. There are two basic types of pumps, work pumps and transfer pumps. Work pumps are generally hydraulic pumps that are used to impart energy to move something, lift something, and create force. They're typically gear, sometimes piston, and normally they're not in need of using a pulsation dampener, although there are some applications as you would get into valves that are opening and closing in the system. We'll be discussing that in another series. The other type of pump is a transfer pump, which is designed simply to move a product from one point to another point. Of the transfer pumps, there are two basic types, centrifugal and positive displacement, typically reciprocating but sometimes rotary. A centrifugal pump uses centrifugal energy, just as its name implies, with a spinning impeller that has vanes coming off the tip of the impeller. Depending upon the type of pump, it can have from 4 or 5 up to several different vanes coming off the impeller. Positive displacement pump imparts its energy by capturing a given amount of liquid in a chamber and then expelling it. Centrifugal pumps produce what is known as a low amplitude but higher frequency pulse, primarily because of the flow coming off the tips of the impeller. This type of discharge is generally considered steady flow in most applications, and the use of a pulsation dampener is not required. Now, pulsation dampener or surge suppressor can be used in other areas when centrifugal pumps are involved in the system, but typically it's start-stop or water hammer, and that again is a discussion that we'll have at a different time. Positive displacement pumps, which capture a given amount of liquid in a chamber and push it out, create what's called a high amplitude but generally lower frequency type of discharge from the pump. And they do that whether the pump is reciprocating or, in some cases, as we'll see a little bit later on, even a rotary type pump. Positive displacement pumps and hose pumps, which are rotary, have uneven flow and pressure. And they're the types of pumps that can most often benefit from the use of a pulsation dampener, surge suppressor, to even the flow and pressure of the discharge of the pump. Today we're going to be concentrating on 3 different types of positive displacement pumps. Air-operated double diaphragm pumps. Now, there are air-operated single diaphragm pumps, but they're not as commonly used, usually in sludge transfer and other applications. So we'll be concentrating today on the more popularly used air-operated double diaphragm pumps. And we'll be talking about metering pumps. Those pumps are diaphragm, piston, even sometimes tubes. And then the last category we'll be discussing are the peristaltic or hose pumps. Now, these are more of a rotary pump because they use a rotor with some vanes or shoes to impart energy to the hose and discharge product that way. First one we'll discuss is the air-operated double diaphragm pump. It consists of a discharge manifold, an inlet manifold, a liquid or water chamber on both sides, an air chamber, and notice that these diaphragms are connected with a common shaft. Then there are 2 inlet valve balls and 2 discharge valve balls. So, being a double chamber or double diaphragm pump, while one side is being pushed, if you will, out by compressed air that's introduced through the pump's air valve, the other diaphragm connected to the common shaft is being pulled in and creating a low pressure area or suction area to bring liquid in. Now, there are various means that are used to trigger this pump shift, but whatever means that is used, when the liquid in one chamber is being pushed out and expelled, obviously the valve ball rises on that side. The other side is creating a partial vacuum and raising the inlet valve ball, so that liquid is flowing into that inlet side while the other side is discharging the product. Relatively simple design become a very popular type of pump to use for various applications. This is a typical curve generated by the discharge of a 2-inch air-operated diaphragm pump. To discuss this curve further, David will explain why it looks the way it does.
Hi, my name is David McComb. I'm a mechanical engineer here at Blacoh. And as Gary mentioned, we're going to discuss these pump curves. This is off of, as he mentioned, a 2-inch air-operated diaphragm pump. It's in a lab environment, so if you have a system and it doesn't look quite like this, then don't be surprised, because what happens downstream, valves closing and opening, and the length of your pipeline is going to affect the amplitude of the curve, and there's a whole lot of factors. Of course, the fluid you're pumping, this is with water. The fluid temperature, the viscosity, there's just a whole bunch of factors there. So, okay, a couple words on our system. We have obviously a pressure transducer because we're getting the data. We're recording at a rate of 500 samples per second, so I've got 500 samples between here and here. That's 1 second. I don't know how well that shows up there, but another thing that we've got here, of course, we have a throttling valve, so it's just a ball valve that is partially closed on our system to create back pressure, and we just dial it to where we want it. Okay, so if we look closely at here, from this point to this point is when one of the chambers in the pump is pumping. And this point from here to here is where the other chamber is pumping. And so if you look closely, you can see that this one, it's kind of quite jagged here, and this one it's more smooth. And then this one, it's jagged again, and then you can see it again there. So from here to here is one pipe cycle, or is one pump cycle. If you look at this, and it's quite jagged kind of all the way along there, that's not electronic noise, that is actual pressure fluctuations in the system. When the valve opens and closes, it's very abrupt, and it creates a little pressure spike that goes through the system. Now, we'll look at some other curves later here. Also, another thing to note, of course, is we have not filtered this data. This is actually raw data, just as it came off the pressure transducer for both this and the dampened curves. Okay, another thing to note about this curve here. I mean, there's a fairly high amplitude of pressure fluctuation. I think it's about 16, plus or minus 16 psi on this one. And this is undampened. This is just basically you hook the pipe up to your pump, and that's what you get. So we'll go back to Gary, and he will continue the discussion on the pump.
So now that we've shown how an air-operated diaphragm pump works and its components, what are the advantages? Why do you use one? Well, there are several. For one, being a positive displacement pump, it's self-priming. As most centrifugals are not, PD pumps are, by their very nature of capturing of liquid in a chamber and expelling it. The process with inlet valve balls and discharge valve balls close off that chamber during the stroke or the retraction of the stroke and create a vacuum or a low pressure area. Obviously, it's air driven. What does that mean? Well, for one thing, you can be using an air diaphragm pump in an atmosphere where there could be sparks or volatile chemicals. In Europe, ATEX is a big standard that must be met by almost every type of piece of equipment that moves. So air diaphragm pumps are very adaptable to that type of application where you could possibly, with a motor or gears or gnashing parts, create a spark, and with the air diaphragm pump, it's not possible. Air also allows the pump to be variable speed and pressure. Now, that's important in many applications because, for example, filling a filter press. You would start out at a lower pressure and generally higher speed, but as the media in the filter backs up or loads up, the pressure increases to keep filling the filter. With an air diaphragm pump, it's very simple. You set the flow rate of the compressed air to the pump and the pressure, and it will automatically adjust to the increasing pressure in the system. Air diaphragm pumps are stallable. When a valve is closed in the discharge of the pump, that pressure created due to the pump pumping into the discharge will build up. When that pressure in the discharge equals the pressure of the compressed air into the pump will stall. No bypass valves are required. No alternate way to relieve the pressure is necessary. It simply stalls out, sits there fully charged with liquid, ready when that valve in the discharge opens to resume pumping, the pump automatically starts. Air diaphragm pumps handle slurries and solids well. Relatively large size solids, there are basically two types of valves in air diaphragm pumps: a ball valve and flap valves. The flap valves open wider so you can use larger solids in them, but both types can handle sludges and slurries and solids. Also, by its nature, it can handle high viscosity products or liquids, because again, we're pulling in the liquid, we're pushing it with the diaphragm out the discharge. We're not going to bog the pump down like a centrifugal would, because they can't spin well in high viscous materials. Air diaphragm pumps, as well as most other PD pumps, handle high viscosity materials. We're talking in the area of 5,000 centipoise. They're also very portable because all you need to do is mount the pump on a cart or something and bring an air line along. Don't have to worry about electrical connections or many of the other things that other types of pumps require to operate in place. Because it's a PD pump or positive displacement pump, and remember, it captures a given amount of liquid in a chamber and then expels it, they tend to be self-priming and high suction lift pumps. An air diaphragm pump, once its components are wetted, and we're talking about the valve balls and seats primarily, often can pull a suction lift of 28, 29 feet, which is very high suction lift capability. Well, now that we've discussed the advantages of an air diaphragm pump, what are its drawbacks? Well, it has a non-consistent discharge flow, both pressure and volume. As David showed you a moment ago, it produces a discharge curve of high amplitude, relatively low frequency, but that high amplitude causes various problems in the system. Also, with this intermittent discharge, the area of acceleration head comes into play. That means that the flow going out the discharge is non-steady, as we've seen, and every time the pump discharges liquid out from its liquid chamber, it has to reaccelerate the liquid that's already in the discharge line. The longer the discharge line, the more liquid or mass must be reaccelerated on every stroke of the pump. Air diaphragm pumps typically also have inlet pressure limitations. They're not high inlet pressure pumps. Most every manufacturer of air diaphragm pumps puts a warning on their pump or in their literature, and it says that maximum inlet pressure for rubber diaphragms is around 15 psi. For their Teflon diaphragms, around 10 psi. So these conditions created by the design of the pump in many cases can be overcome or negated by the installation of pulsation dampeners and inlet stabilizers, because they will turn the flow downstream of the dampener into near steady state. Now, it's important to locate the dampener right at the discharge of the pump, we say within 10 pipe diameters, because you won't get the effect of the dampener until the flow is past the dampener. But when you have a dampener sized properly and charged properly, you virtually eliminate acceleration head problems. Vibration is gone because the flow is steady and therefore the pressure is steady. And on the inlet side, using an inlet stabilizer, you will absorb or accumulate any pressure limitations or spikes that are created, which incidentally are created because of the valve balls opening and closing and starting and stopping the flow into the pump. So most of these drawbacks can be overcome by the proper installation of some sort of a pulsation dampener or inlet stabilizer. David's now going to discuss this latest iteration of pump curves, which show both dampened and undampened performance.
Okay, here we've got a graph that's got the undampened coming off of the pump, and then here's the graph with where we added a dampener into the pump, into the line. Now, as Gary mentioned a little bit, the location of the dampener is very important. You want it as close to the pump as possible, because you have a volume of fluid between the pump discharge ball and the dampener. And the less fluid you have there, the less gets accelerated and decelerated, so you have less of an effect if it's farther away. So, and we recommend within 10 pipe diameters of the discharge. Better if you can get it right at it. You can see there is some fluctuation here, but much less than before. In this case, we are 3.5 psi fluctuation, and before the dampening, we were plus or minus 16 psi. Generally, that's is great for most applications. Some applications it's not. We're going to go into sizing calculations in a little bit. If you're looking at a graph like this, it tells you something about the pump. Perhaps maybe there's one ball is different than the other. Maybe one's leaking a little bit, so it's a slower. It's moving a little bit less fluid on one side than the other. Maybe one is closing really positively, and that's why you're getting this really big spike here. You know, there's a whole bunch of factors there. All right, if you notice here, you will look at the valleys in the graph here. We're about 15 psi on the low side, and then it's going all the way up to about 45, 46 psi there. That's a pretty hefty variation. Also note that between this curve and this curve, the valve that is creating the back pressure is in the exact same place. We haven't moved it. And the dampen curve is running about 30 psi, and we've virtually eliminated the acceleration head loss. We've minimized it. If you want less variations than this, then you need a larger dampener. And like I said, we'll go through those calculations in a little bit. So, with this curve here, the pressure fluctuations on the outlet side of the dampener have been reduced because we are no longer accelerating and decelerating the mass of fluid in the system piping. So therefore, we have minimized the acceleration head loss. It's also notable that the pressure does not totally correlate to the flow rate. It pretty much mirrors it, but the pressure is caused by the change in the flow rate. All right, now let's switch to the inlet side of the pump. And we've got a graph here on the screen of what the pressure spikes look like on the inlet side. I mentioned Gary had mentioned a little bit ago that air-operated diaphragm pumps don't like a lot of inlet pressure. As he mentioned, 15 psi. Well, this here is the undampened curve, and you can see we're going way above 15 psi. This is on a 3-inch air-operated diaphragm pump. There is 15 feet of line from where we're pumping the fluid to the pump itself, which isn't very far. So the further you get, the worse this is going to get. We have an inlet stabilizer that we've added to this system, and this is what you get with the inlet stabilizer in place. Now, you look at this and you say, well, okay, we're still getting some pressure fluctuations, and the question, of course, is what is that from? Well, we can't get the dampener right at the balls of the pump, so you have a pretty good the mass of fluid that's in the line. Well, and then we have the dampener, and then there's still a little bit of mass of fluid between the dampener and the check valves in the pump. And so when those check valves close, they close pretty much instantaneously or very quickly, and then you get a little bit of a water hammer effect, and that's what this is coming from. If we could install the dampener right at the balls, you would probably see a line that looked more like the other one. But if you look at this, we are way down here in vacuum of about, 7 psi, and then we're going all the way up there to 26, 27 psi. It's quite high, and then here we're running at an -5 or -6 to about +5, which is very doable.